Hello and welcome. In this video, we're going to start taking a look at the world of optimization in multivariable calculus. Now, in previous videos, we've taken a look at the gradient, and we know how the gradient is a tool for being able to calculate the directional derivative of a function in whichever direction we choose. But also more than that, the gradient vector at any given point gives us a direction in which the rate of change of that function is a maximum. So it's kind of maybe this next logical step to be able to figure out where that function has maximum or maybe minimum values. We call these extreme values of a function, or simply just extrema. And if you think back to first year calculus, that single variable idea, we had different kinds of maximums and minimum values. We could either have a local maximum or a local minimum, or we could have an absolute maximum or an absolute minimum. Now, we do have some fairly similar definitions here in multivariable functions. So let's start off with that. If we have a function f of n variables, and let's say p naught is some point in the domain of f, and it would be an n tuple. That would mean it would have some sort of coordinates a1, a2, all the way up to an. Then if we want to start taking a look at local extrema, we have a local minimum or a local maximum. For local minimum at p naught, that just means that if we evaluate f at the point p naught, it is less than or equal to f evaluated at any point near p naught. Same thing with a local maximum. But here, f evaluated at p naught is greater than or equal to f evaluated at any point near p naught. For absolute extrema, we simply just need to change that last little bit of wording there into any point p in the domain of the function. So for instance, an absolute maximum would be if f evaluated at p naught is greater than or equal to f evaluated at any point in the domain of f. Now in this video, we're going to be focusing on local extrema. We're going to be just trying to figure out where we might find local extrema, and then be able to determine if they might be a local minimum or maybe a local maximum. But we need to come up with a method for finding the points first. And it's actually very similar to how we found points in single variable calculus where we had local extreme values. This theorem may seem kind of familiar. If f has a local maximum or a local minimum at a given point in Rn, then either the gradient of f evaluated at that point is the zero vector, or the gradient of f evaluated at that point is undefined. This is essentially an extension of Fermat's theorem for single variable calculus. In single variable functions f of x, we said that if f of x has some sort of local maximum or local minimum at x equals a, and if f prime of a exists, then f prime of a equals 0. So that pretty much told us that's a great way to find local minimum or maximums. But it's possible that you could have a local minimum or maximum when the derivative doesn't exist. So these are the same two kind of cases here for multivariable functions. Instead of the derivative of the function, though, we have the gradient of the function. Either equals 0, in this case the zero vector, or the gradient doesn't exist. In single variable calculus, we were looking for critical numbers, but now in multivariable calculus, we're looking for critical points. These are points where the gradient is equal to the zero vector, or the gradient of f is undefined. Now, not only is this kind of an extension of Fermat's theorem, we can prove it using Fermat's theorem. Essentially, what we can do here is, let's say that we want to leave all but one of these variables as constant and vary just one variable. So let's suppose that we could just define some sort of function g of x1. That's our first variable. And that's defined to be f evaluated at x1, and all of the other values of x are just plugging in the values a2, a3, all the way up to an. Well, this now makes this a single variable function. And that single variable function would have an extreme value at x1 equal to a1. By Fermat's theorem, g prime of a1 has to equal 0, or g prime of a1 is undefined. But g prime of a1 is actually a partial derivative of f. f1, that's the partial derivative of f with respect to x1 at a1, a2, all the way to an. So that proves part of the theorem. We know at least that particular partial derivative is either equal to 0 or undefined. If we repeat this process for all the remaining variables, then we know that either the gradient, which consists of all the partial derivatives, equals the zero vector, or at least one of these derivatives is undefined, in which case the gradient vector is undefined. Well, with this theorem, we can at least see where we could get local minimums or local maximums. We really only have two options for where they can occur at. But that doesn't mean that at every point where the gradient equals the zero vector or where the gradient is undefined gives us a local minimum or maximum. In fact, what we really need to establish here is some method for classifying critical points. We had a very similar method for classifying critical numbers in single variable calculus, but here let's start focusing maybe on functions of two variables. For example, we could think about the function f of x comma y equals x squared plus y squared. Now, we can see right off the bat that if we were to take the gradient of that function and plug in the point 0, 0, that we get the zero vector. And we know what this graph looks like. It's an elliptic paraboloid opening upward. And at that particular point where the gradient equals 0, we have a horizontal tangent plane. It's just the vertex of that elliptic paraboloid. So we can see right away that in this particular example, we would have a local minimum. Now, this minimum is actually a little bit stronger than that. We also know it's an absolute minimum just based off the fact that this is an elliptic paraboloid. But in this video, we're going to be mostly focusing on finding local extreme values. So let's take a look at another example. What if we were to take a look at the function f of xy equals 4 minus the square root of x squared plus y squared? Well, that is a cone that has just been shifted a little bit. And if you wanted to compute the gradient of this function, and then maybe just plug in the point 0, 0, then you're going to get a point at the tip of this cone where the derivative is undefined. However, we can see by the graph of this function that at that particular point, we actually have a local maximum. But there are cases where the gradient of the function is either equal to the zero vector or is undefined, and we have neither a maximum or minimum value. We just need to simply take a look at the hyperbolic paraboloid x squared minus y squared. It's pretty easy to compute the gradient of that function and plug in the point 0, 0 and find that we end up with the zero vector again. But we've seen this graph before, and we know that at that particular point, we have two cross sections. One is a paraboloid opening upward, z equals x squared, and one is a parabola opening downward, z equals negative y squared. So at this point, we can neither have a local minimum or a local maximum. We actually call this a saddle point. We need to be able to classify each of these critical numbers as one of these three options. And rather than the second derivative test from first year calculus, we have the second partial derivatives test. For the second partial derivatives test, just due to the higher complexity of this test for multivariable functions, we're going to focus on functions just of two variables. And of course, we're going to need to compute second order partial derivatives, fxx, fxy, and fyy. But more specifically, we want to have continuous second order partial derivatives. Now, if those second order partial derivatives are continuous, that also implies that the first order partial derivatives are continuous. And that means that we're really only going to be focusing on critical points of the form where the gradient of f at a point AB is equal to the zero vector. In order to classify these types of critical points, we compute something that we call the discriminant. And that name, discriminant, should hopefully be kind of familiar from way back in algebra days when we were just trying to solve the quadratic equation. The discriminant was that b squared minus 4ac that told us if we ended up with two real roots, one repeated root, or complex roots, no real roots. In this particular case, for a function f of x comma y, the discriminant is fxx times fyy minus fxy squared. It's written in terms of these second order partial derivatives. But perhaps instead of remembering that formula, it's better to remember this actually as a determinant of a 2 by 2 matrix. fxx, fxy, fyx, fyy. And because of these continuous second order partial derivatives, fxy and fyx are going to be the same. Now this 2 by 2 matrix that we have inside this determinant calculation, it's not just for convenience. That is actually how we conduct the second order partial derivatives test for functions of more than 2 variables. Instead of a 2 by 2 matrix, we could have an n by n matrix though. That's called the Hessian matrix. And we could talk about that in a future video, but it's definitely beyond the scope of this particular video. We're going to stick to just functions of 2 variables for now, which is also helpful. We can kind of visualize that as just being a surface. Once we've computed the discriminant, then we can plug in this particular point that we're testing, a comma b. And we have 4 cases for classification. If this discriminant ends up being positive, then in case 1, we'll also have to test the second order partial derivative fxx at that particular point. If that's also positive, then kind of similar to our second derivative test from single variable calculus, this gives us a local minimum. We can essentially assume that it has a shape similar to an elliptic paraboloid opening upward. Now, in case 2, if the discriminant is positive again, but this second order partial derivative fxx at the point AB is negative, then we have a local maximum value. We can kind of assume that the shape at that point is similar to an elliptic paraboloid opening downward. If the discriminant is negative, though, we don't have to test any of the second order partial derivatives afterwards. That just tells us that at that particular point, AB, comma f of AB, that's a saddle point. Unfortunately, if this discriminant equals 0, then we cannot use the second partial derivatives test to classify that point as one of the 3 options. Now that we've got this test, it's pretty easy to classify each critical number as one of the 3 options. The tricky part can sometimes even just be finding the critical points. This kind of equation is a vector equation where we compute the gradient, which has 2 components in this case, fx and fy. We set that equal to the 0 vector, which also has 2 components. That gives us 2 equations, fx equals 0 and fy equals 0. But they don't have to be linear equations. So the solution to this system of potentially nonlinear equations can have many solutions. So let's take a look at a couple different examples and see how we can find critical points of this form and also classify them. Let's start off by trying to find and classify all of the critical points of a fairly basic polynomial in x and y. Now, this is a polynomial where you can determine the degree by looking at each term. The first term has a degree of 3, it's got an x cubed. The second term has a degree of 2 because it's x to the 1, y to the 1. And then our third term is also degree 2 because we have a y squared. That makes this overall polynomial a cubic polynomial in x and y. Because it's cubic, we might get multiple local extreme values. We might find maybe a local minimum, maybe a local maximum, maybe a particular saddle point in there. So we're going to have to classify them. If it was simply just a quadratic polynomial in x and y, then we wouldn't really find much more than just a elliptic paraboloid or a hyperbolic paraboloid. We wouldn't really have much to classify there. So let's see if we can find the equations that we need to solve first to get these critical points and then classify them. We know we're never going to get points where the gradient of f is undefined for a polynomial like this, so we're just going to look at points where the gradient of f is equal to the 0 vector. And make sure it's not just the gradient of f equals 0, because that would be saying that a vector equals a scalar. That wouldn't be correct. Now this particular equation can be split up into 2 parts. The partial derivative of f with respect to x, that's 12x squared plus 12y. That would have to equal 0. And a second equation where the partial derivative of f with respect to y, that would be 12x plus 12y, is also equal to 0. Now, each of these equations nicely has a common factor of 12. And if the right-hand side equals 0, then we can simply divide both sides of the equation by 12 and simplify the equations out. Equation 1 could simply just turn into x squared plus y equals 0. And with equation 2, we would have x plus y equals 0. Or maybe we actually just want to do a little substitution and say equation 2 is y equals negative x. So let's start by taking that equation 2, which is pretty easy, and substitute it into equation 1. When we take that y equals minus x and plug it into x squared plus y equals 0, then we end up with an equation of one variable. X squared minus x equals 0, which we can simply factor as x times x minus 1 equals 0. Make sure not to just divide by x or something like that, because then you'll be missing a solution where x could equal 0. It's better always to just try and factor if possible. This gives us two particular solutions for x. Either x equals 0 or x is equal to 1. Now, because we found these two values of x by substituting equation 2 into equation 1, we have to trace our steps back here. Tracing backwards, we know that in this particular case, y has to equal negative x. And that means that when x equals 0, y has to be 0. And when x is equal to 1, then y has to equal negative 1. This gives us our two critical points, 0, 0 at the origin, and 1, negative 1. Now we're ready to start classifying each of the critical points as a local minimum, a local maximum, or a saddle point. Just remember, we already have the first order partial derivatives. To get the second partial derivatives, we're going to take the derivative of fx with respect to x again, but we'll also have to take the partial derivative of fx with respect to y. And fxy and fyx should be the same. Let's try computing each of these second order partial derivatives. The discriminant d is the determinant of fxx, fxy, fyx, fyy. If we want to take the derivative of fx with respect to x, then treating 12y as a constant, we will end up with 24x. fxy is where we take the partial derivative of fx with respect to y. So we'll treat 12x squared as a constant, and then the derivative of 12y is simply equal to 12. It's always nice to check that the derivative fyx is also the same, and that will be where we take the partial derivative of fy with respect to x. Sure enough, that is also equal to 12. Lastly, we're going to have to take the partial derivative of fy with respect to y. That is also 12. Now it's a matter of calculating the determinant. Now, the determinant of a 2 by 2 matrix is simply just the main diagonal 24x times 12 minus the reverse diagonal 12 times 12. This gives us the discriminant 288x minus 144. Now that we have just a general expression for the discriminant, it's easy to plug in the points 0, 0, and at that particular point, since x is equal to 0, the discriminant is simply just equal to negative 144. Since that is negative, we don't have to do anything else. That is simply case 3 of our second partial derivatives test. And in case 3, that tells us at 0, 0, we get a saddle point. Now, our function evaluated at 0, 0 gives us a z coordinate of 0. So this is a point where we have exactly the origin. 0, 0, 0 is our ordered triple. And that point is on the surface, and it's a saddle point. What about the point 1, negative 1? Here, x is equal to 1, and we'll plug that into the discriminant. And that would give us the discriminant equal to 288 minus 144, and that gives us 144. Now that's positive, so we haven't quite figured out exactly what kind of a critical point this is, but we know that we get a local minimum or a local maximum. We'll have to do the other part of this test and determine the value of fxx. Well, that's 24 times 1, that's 24. That's positive. So at the point 1, negative 1, what we essentially have is a shape similar to an elliptic paraboloid opening upward. And this is the minimum value of it. So if we plug 1, negative 1 back into our function, and we evaluate the function, we end up with a value of negative 2. And that must be a local minimum value. Now, I do find it helpful to maybe just visualize what that would look like, but it's always tough to try to sketch this kind of function by hand. So let's turn over to Maple and see if we can use that as a tool for seeing visually that saddle point and the local minimum. So over here, I've got our plots package and just a simple plot3d command of the function z equals 4x cubed plus 12xy plus 6y squared. And don't forget that when we have two variables side by side here multiplied together, to either include a space or a little multiplication dot, one of those two options. Now, it may be best to maybe just zoom in around those 2 points. So let's start with x from -1 to 2 and y from -2 to 1. Now, if we take a look at this surface, we can kind of see that it has a little bit of a bowl shape from the side. And if we look at it from a different angle, we can also see a bowl shape from this particular angle. In fact, it's a bowl everywhere. At that particular point, 1, -1, then we see that we've got essentially the same kind of shape as an elliptic paraboloid opening upward. That's a local minimum value right there. But over here, we have a saddle point. It's kind of like a local maximum if we look at it from one particular profile view, but it's also a bit like a local minimum from another profile view. And that's exactly what we would consider a saddle point right there. And we can see it's when x equals 0 and when y equals 0. In this next example, let's once again find and classify all critical points of a cubic polynomial. Only this time, when we try to find all of the points where the gradient of the function is equal to the 0 vector, we kind of get a little different set of equations with more interesting solutions in a way. When we want to set the gradient of g equal to 0, well, let's just split that up into two equations right off the bat. We'll have the partial derivative of g with respect to x equals 0. That's 3x squared minus 12x minus 36 equals 0. And for our second equation, we'll have the partial derivative of g with respect to y equal to 0. And that's 3y squared minus 18y. Now, we can factor each of these equations, but you may notice that in one equation, we have a polynomial in terms of x only. And in our other equation, we have a polynomial in terms of y only. So there's no way to use substitution or elimination with these two equations. We'll just solve each of them separately. Our first equation can be factored. We can take a common 3 out. And from there, we're left with a quadratic x squared minus 4x minus 12. That can be factored into x plus 2 and x minus 6. So we have two solutions to that equation, x equals -2 and x equals +6. But like I said, you can't plug either of those two values into this other equation and get a specific associated solution for y. Instead, we can just solve the equation on the right separately. In this case, we can factor out 3y in common, and that leaves us with another factor of y minus 6. So the solutions to that equation are y equals 0 and y equals 6. Well, what kind of points would we have that would satisfy both equations? Really, we have some freedom. The solutions to this first equation only are solutions for x, and y can be anything. That means we can choose either of these values of y and pair them up with each of the values of x. That leaves us with 4 combinations. The 4 points we have to consider are -2, 0, -2, 6, 6, 0, and 6, 6. So obviously this is very different than that first example. In that first example, we actually had to determine the solutions by using both equations simultaneously. That really limited how many solutions we could get. But here we had 2 of these quadratics, each of them with 2 solutions. 2 times 2, that gives us 4 solutions. And that'll happen especially when you have 2 equations with separate variables. You're going to get quite a few different combinations of potential solutions. Once you've got that part of the process done, though, nothing else is really going to change here. We just need to use the second partial derivatives test to classify all of the critical points. Now, in this case, our discriminant is the determinant of this 2x2 Hessian matrix where we have gxx, gxy, gyx, and gyy. Hasn't really changed other than, in this case, our function is g. Now, notably in this case, the mixed second order partial derivatives, gxy and gyx, are both going to be 0. And gxx and gyy are both going to be linear. So we have this 6x minus 12 and 6y minus 18 as those second order partial derivatives. Let's go and calculate that determinant. Well, that's going to be easy. It's just simply the main diagonal minus 0. And you'll notice that that is literally just the product of gxx and gyy in this particular case. So it's going to be maybe easier if we don't expand that out and we just determine if each of those factors is positive or negative and figure out if the discriminant is positive or negative as a result. Let's start with our first point, negative 2 comma 0. Well, if we just let x equal negative 2 in this first factor, then that factor is negative. And if we let y equal 0 in the second factor, then that factor is negative. Two negative factors put together tell us that the discriminant is positive. And in that case, we still have to check and see whether or not gxx is positive or negative. But since gxx is actually that first factor, we already know that that is negative. That tells us that we have a local maximum when x is negative 2 and y is 0. If we plug those values into the function, then g is equal to 40, and there's our local maximum. Let's go on to the second point here when x is negative 2 and y is 6. This first factor, once again, is going to be negative, but the second factor when y is 6 is going to be positive, and that tells us immediately that the discriminant is negative. There's nothing else that we have to check. We have a saddle point. And when x is negative 2 and y is 6, that gives us a z value of negative 68. There's our saddle point. As for our third point, we have x equals 6 and y equals 0. That means that this first factor is going to be positive now, but the second factor is negative. And when we take the product, that tells us that the discriminant is negative again. This gives us a second saddle point. When x is 6 and y is 0, you can check and see that z is equal to negative 216. Finally, let's go to our last point, where x and y are both equal to 6. In that case, both factors are positive. That tells us that the discriminant is positive, and that first factor, 6x minus 12, is actually gxx, and we already know that that is positive. Since both of those values are positive, then by the second partial derivatives test, we have a local minimum when x and y are both equal to 6. And if we plug that into the function g, then g attains a local minimum of negative 324. Now, as before, let's see if we can visualize this, and we'll use Maple to do that. So in this case, I'm actually going to define the function g of xy, x cubed plus y cubed minus 6x squared minus 9y squared, all minus 36x. And we'll just plot g of xy on a range that's hopefully not too far away from those 4 points. Because as you can probably imagine with a cubic polynomial like this, it is going to grow off to infinity if I zoom out too far. So let's see what we got. Sure enough, we have a local maximum. You can clearly see that hill there, and that is when y is equal to 0, but x is equal to negative 2. There's our local maximum. Now, we also have a local minimum right over here when we have the point x and y both equal to 6. You can see that right there. And it kind of has a similar shape, at least in a little local area, kind of like an elliptic paraboloid. It's just pointed down there and it's pointed up here. But we have two saddle points. You can see sort of a quadratic looking shape here and sort of a quadratic looking shape there. But they're going in opposite directions, and that gives us a saddle point. And sure enough, here's our other saddle point. Now, you can actually take any point on this surface and approximate the overall shape of the surface with a quadratic approximation. We've done linear approximation already. Quadratic approximation is even better. It's basically taking this kind of surface and approximating it with a quadratic polynomial. And a quadratic polynomial will have a shape kind of like an elliptic paraboloid in certain cases, where that's when we get maybe a minimum or a maximum. But a quadratic polynomial in x and y can also look like a hyperbolic paraboloid. And if that's the case, then that might be where we get saddle points. Now, extend that idea. You can actually do this with functions of more than two variables. You can approximate them with a quadratic polynomial. And That is how we actually extend this second partial derivatives test from functions of two variables into functions of more variables, is through quadratic approximation. That Hessian matrix just gets bigger and a little bit more interesting to go and analyze to find out what kind of a extreme value or saddle point we get. But that's not for this video. That would be something, if you're interested, you can go and dive into that. Hopefully for now, you've got kind of a pretty good overview of how we've taken the concepts of optimization from a single variable function into a function of two variables and even beyond now. We're going to be looking at other forms of optimization for specialized problems in future videos, so stay tuned. Thanks for watching, and I'll see you in the next video.